Test. Good. And then this thing will hopefully connect at some point. I don't care. Let's see how it goes. It says it's streaming now, but then it's offline when I do the dashboard thing. So, there it is starting. Okay, good. So it says offline again. No, it's working. All right. So differential equations. We are supposed to solve differential equations now. Last time we solved the population problem. We are going to look now at the, you gotta lower it down. We have to now solve the differential equation with initial conditions. And initial conditions are going to be the ones that help you compute the constant which was unknown in the differential equation. So I'm going to actually work out one of the examples that is in your homework section. If I hit the problem that it's done, or that is posed as the homework problem, then you just pick another problem and work on that. Actually, you know what? Let's do simple stuff first, and then we'll go from there. So how about this? Let's say your differential equation is y prime equals to, let's say, 3y, and initial condition is that y of 0 is equal to 7. All right, that's it. So over here, this is your differential equation. We said the differential equation is the equation that has function and its derivatives. And we also have the other one, which is y of 0 equals 7, which is our initial condition. So initial condition. So what we are going to do now is solve our differential equation, and then we are going to use the initial condition to compute what we call particular solution. So let's take a look, and all this terminology will fall in place as we go. So y prime, we are going to use Leibniz notation to write that out. Say dy dt is equal to 3y, and then we use separation of variables. We use separation of variables to solve this, which means that dy over y is going to be equal to 3 dt. There is no reason for me to move the 3. You can just leave it where it is. And once we separate the variables, we can integrate both sides, which will give us ln of absolute y on the left, because that's the dy over y, right? And on the right, I have the integral is 3t plus c. Then we exponentiate both sides, so e to the ln of y. E and ln x are inverses of each other, which means we just get y on the left-hand side. And on the right-hand side, I have e to the 3t plus c, which we can write as e to the 3t times e to the c. And we said that this e to the c is a constant, so you can just call it maybe some capital A if you want to. You can pick any value, any number there. So now what we did is we found that the function y of t is equal to a e to the 3t. And if I box this, this is what is known as a general solution. General solution meaning that you have this constant a, which means that depending on what that a is, you can have a function which is the particular solution. So if I pin down that a is 2, then you only have 1. Right now it's a family of functions. A is the y-intercept for e functions. So technically what you are looking at is a family of these depending what you set a to be. Right? Any of these values could be a. So that's why it is considered as a general solution. What I can do is I can use initial condition. I believe I said y of 0 is 7. There we go. So now we use y of 0 is 7. Now this y of 0 is 7. This 0, that means if t is equal to 0, y is equal to 7. We plug that in our general solution. And as you can see, the only variable would be a. You would be able to compute how much a is. So 7 is equal to a times e to the 3 times 0. 3 times 0 is 0, so you have a times e to the 0, which is a times 1, which is a, and you just got that a is 7. So now we can write y of t is equal to 7e to the 3t, and this solution is known as particular solution. You can call it the solution, right? Because it is exact one, it is exactly one function. And we know that it's a is 7. So if I am to draw exponential function like this, we know that this value over here is 7. And there are no other functions that fit this. Like up there, we had the family of them because a was whatever. Now a is exactly 7. So I have that. And this is the problem solved. So as you can see, the separation of variables that we did here is giving us the general solution first. And once you have the general solution, you have the option of computing how much a is using the initial condition if the initial condition is provided. In this case, I provided you with the initial condition, which means that you were able to compute the value. All right, so that's the initial condition. Now, initial condition doesn't have to be, right? You associate the word initial as in the beginning of time because t is equal to 0. But it doesn't have to be. I can set t to be any value. Could be 1, could be 100, could be negative 1/2. It doesn't matter. You can always, if you're given a point, you can come up with the value that goes through that. The next part over here is the solution to the first order linear differential equation, which you can derive through separation of variables. And it's listed as a formula, which you can memorize, or you can just solve this anytime when you're working on it. So, solution of a first order. Does anyone remember from last class what the first order means? First order differential equations? DE, differential equation. First order means only first derivative is present. Linear means no squares on derivatives or y or dependent. No squares on any of the dependent variables. So the general solution of the first order equation. So the first order equation is given by y prime of t is equal to ky plus b. So you see everything is linear, everything is first order. There are no squares anywhere. So this is the equation. So this is differential equation over here. And the solution for this is y of t is equal to ce to the kt minus b over k. That's the solution. Now, it is an interesting question for the test to prove this, right? And how do you prove this? Well, just run separation of variables. You will take the ky plus b as a unit, put it down, and so I can actually start this for you, and then you can have fun at home solving it. So dy dt is equal to ky plus b. Now, ky plus b is 1 unit, so when you do separation of variable, you go dy over ky plus b is equal to dt, and then you integrate both sides. I'll put 3 dots, and then those of you interested in this proof, you can easily solve it. Obviously, some kind of ln is going to be there, and then some constants popping up. and you will be able to solve this. So it's just a standard procedure. The integration could be a little bit trickier, but just remember that k and b are constants, and you get to copy them and so on. So technically, that takes care of that part. Now we want to use this. We want to use this in a problem. Now the textbook provides only 4 examples, but technically you guys can come up with anything else. So here's what the textbook says. Differential equation du over dx, which means x is the independent variable, is equal to 2u plus 6. And they also give us condition u of 1 is equal to 6. Right? So now you know what the solution is, right? The solution was y of t is equal to cekt minus b over k. Right? That was the solution that we have defined up there. We know that this value over here is k. We know that this value over here is b. Guys, you just need to plug this stuff in. If you have the solution for the entire family memorized, then you just get to plug in. Do you have to memorize it? No, because you can run separation of variables and solve this, right? It's just a time saving if you memorize the solution. So what is my u of x function? Because I obviously have to use those variables. This is just what we memorize, the formula. U of x is equal to ce. Now k is 2, so 2t, minus b is 6 divided by k, which is 2. Now 6 divided by 2 is 3. So u of x is equal to ce2t minus 3. This is the general solution. But we don't care about that. That's what I said. Please pay attention. Thank you. It is x. I'm used to t's. All right, there we go. Thank you. So it is, yes, it's an equation in terms of x. So x is independent variable. All right. So now we use the initial condition. U of 1 is equal to 6, which says that 6 is equal to ce to the 2 times 1 minus 3. Move 3 to the other side, you get 9 is equal to ce squared, and you see that c is 9 over e squared. So what is the particular solution? It's u of x equals to, instead of c, I write 9 over e squared times e to the 2x minus 3. Now, for those of you that are a little bit better with algebra, right, you know that this e is a negative 2 exponent, and then you can combine the exponents. So if you really want to be cool, you will just write 9e to the 2x minus 2 minus 3. And you can even factor that 2 over there. It's not necessary, but it looks nicer. X minus 1 minus 3. For a particular solution. And this is a particular solution. This is what we're looking for. Particular solution. How do we check equations? How do we check if the solution to any equation is correct? We plug this in the equation. But we can't really plug it in the equation directly because the equation actually has the derivative. So we have to take the derivative to plug it on the left side, and we plug it as is on the right side. And then if they work out to be the same, we're good. If they don't, something is wrong. You have to go back and do problem from scratch, or check it, or find what's wrong. So let's check. Let's check. So how much is du dx? Well, we have to differentiate this. The derivative of e to the, so copy 9, derivative of e to the 2x minus 1, that stays the same, times the derivative of the function up there, so that's 2 in the chain rule, and the derivative of minus 3 is 0, so just don't worry about that. So it works out to be 18 e to the 2x minus 1. That's all it is. That's the derivative. And that's the left-hand side. So now remember that the differential equation was du over dx is equal to what? What was it? 2u plus 6. So 2u plus 6. You just plug stuff in. Instead of du dx, you have 18 e to the 2x plus 1. On the other side, you have 2 times u is 9e to the 2x minus 1 minus 3. And then you also have plus 6 at the end, because right, that's the plus 6 that you put at the end. So everything is plugged in. You have 18 e to the 2x plus 1. You can already see it, but I'll write it. 2 times 9 is 18 e to the 2x. Oh, I put plus 1. And then you have 2 times negative 3 is minus 6 plus 6. They cancel, and there you go. 18e is equal to 18e, right? This is how you know that your differential equation solution is correct, because it worked out. And this is the part where you should realize what the differential equations are. It's the higher order of equations than what you used from before. When you solved any equation prior to differential equations, your answers were numbers. X equals 7, x equals a half, x equals to a knowing decimal, or e to the 3. It doesn't matter. So if you have an equation x plus 3 equals to 5, we subtract 3 because that's the opposite operation, right? We get x equals to 2. Solution is a number. Differential equation, which we had, which is du over dx is equal to 2u plus 6, as the answer had u of x is equal to 7e to the 2x plus 1 minus 3. Is that the solution? Yep, minus 3. And you guys see that the solution for differential equations are functions, where the solutions to your good old equations from your algebra courses and pre-calculus courses were numbers. So this is the higher order, right? But the same rules follow. If you want to check the equation with numbers, you take that solution, plug into every x, you get 2 plus 3 is 5, which is 5, which is good. On our case, when the solution is a function, you get to differentiate that and plug back in the differential equation and then check it that way. And that's exactly what I did in blue. That was a check procedure. And hopefully when you take differential equations class, right, you will be checking every problem, and then you would know what they are. Yes? Because it is. There is nothing else. If you look at the, so the question is if I have du over dx is equal to, let's say, 3x plus 5, and I want to do separation of variables, how do I know what do I move? Well, you need to separate variables and put all u's on one. Sorry, not 3x, 3u. There can be equation that looks like this as well. This is a very easy equation, actually, 3x plus 5. Let's take a look at both of these. So the one on the left is the one that we just did. And if you take a look, the only things that you can move on the right-hand side is you can say minus 3u on both sides, which would give you something that is useless, right? Because it will look like this. So really can't do anything with that, so I'm just going to put red X, not good. The other thing you can move is 5. So that's going to be du over dx minus 5 is equal to 3u. Again, variables are not separated, right? Because that's what algebra allows us to do. Now, if I decide to use 3u plus 5 as a unit, Well, in that case, if that's all one unit, then I can swap dx and that one, right? Because it will be over here is over 1. And I would obtain du over 3u plus 5 is equal to dx. And now you see that all u's are on one side and all x's are on the other side, which means the variables are separated. So this is me leading you through correct and bad, correct and bad choices. Now the equation on the left, on the right, sorry, is having dx, right? And if you have dx over here, that dx goes on the other side and variables are immediately separated. So du is equal to 3x plus 5 everything times dx. And now you can immediately do integral on both sides, and you see that this is quickly u is equal to, and you just integrate this in terms of x, you get 3/2 x squared plus 5x plus some value c, and this problem is solved already, right? So you play with algebra, making sure that if you're doing separation of variables, all u's are on one side, all x's are on the other side, no exceptions. Which we did not achieve that with those two that I x'd out, right? Yeah. Because x stayed on the left together with u's. I mean, the third line is actually the second x'd out line is a complete disaster, right? Because it has u's on two separate sides, the x is mixed in. So answers the question, right? Perfect. And but there is a whole bunch of problems. Now, guys, this is just the cheapest, as I said, the cheapest possible method of solving differential equations. When you take the class, you will learn integrating factor and variation of parameters and all of these other cool techniques for solving first and second order and whatever other order leading into non-linear dynamical systems and so on in the last section. Laplace transforms and so on. The class has a lot of cool techniques for solving differential equations. So when you go there, separation of variables will be with you on the first day, and then maybe pops up here and there eventually. You know, you learn other techniques that are cool. So that takes care of the. That takes care of that. Now we're going to take a look at directional fields, also known as slope fields. This is something that you're not used to because it's new stuff, new concept, and it uses the idea of slopes. The interesting part with this technique is that you guys can solve differential equations without solving them, what we say analytically, right? Grinding through all this algebra and calculus. You can actually create these directional fields that will guide functions through. And I'm actually going to just switch quickly to the textbook so you guys can actually see a directional field at work. So what you see over there on that graph is that you have the first quadrant of XY plane, and in that first quadrant of the plane, you can see the blue and the red lines and all the other colors. But you also see these small black lines, the short ones. Those lines are the ones that guide how the graphs have to behave. And any particular line that you pick, if you pick the red one, right, the one that goes kind of diagonally, observe that its shape is looking for the path, so it's always perpendicular to all of those little lines. And any other line would do the same thing. You see the one, the blue, that's all the way on the bottom, it's kind of trying to fit through all of those little lines. So those shorter black lines are there, and they look like guides. They look like guides for these solutions. Now, generating this field is extremely simple. It doesn't use calculus. It doesn't use any of the advanced techniques. It just gets you to the knowledge that the slope is the slope of the line, which is the derivative from your differential equation. And in addition to that notion that you can pick any value and then you compute what kind of slope you have to put on it. So let's take a look. So direction fields. Try not to fall asleep because serious stuff. So let's have a differential equation. Let's say y prime is equal to 1 over x. Let's see how the solution. Yes. Oh, I have to switch back. All right, fine. Here's the tablet. There it goes. So direction field. Let's say this is our differential equation. This is our differential equation, and we want to see how the solution for this looks like without actually finding the solution. So what do? I realize that this y prime is dy over dx is equal to 1 over x. Now this part here, by calculus 1, is the value of the slope of the line. It's m. It's slope. So what can I do? I can pick a value for slope. And then I can compute from there the line on which that slope needs to be drawn. What does that mean? Well, here we go. Pick m, which is our derivative dy dx, to be 1. You pick that value. That will produce that 1 is equal to 1 over x, from where x is equal to 1. Pick m equal, which is dy dx, let's say 2. In that case, 2 is equal to 1 over x, from where x is equal to 1/2. Pick m equals dy dx equal to 3. From there, 3 is equal to 1 over x, from where x is equal to 1/3. We see the pattern, right? How about trying to pick different values? Let's pick m equals, so pick m equals to 0. Well, that tells us that 0 is equal to 1 over x, from where 0 equals 1, which makes no sense. So yeah, we don't get to pick that value, right? Can't have a 0 slope. Now, for what kind of functions you can't pick 0 slope? What kind of function does not have a 0 slope anywhere? Exponential is the one of them. But what is so specific and interesting about exponential function so it doesn't have that slope? Or for any other matter, other functions that don't have a slope of 0 anywhere showing up. What is true for those functions? They could equal 0. I can move the the e to the x to e to the x minus 2, and then it's going to intersect x axis, which means y equals 0. So yeah, they could reach 0. Guys, where is the concept used? Where is the concept used of 0 slope? For what kind of application? Yes, finding the maximum and minimum, right? If you are trying to find a min and max of a function, you set the derivative, which is the slope, equal to 0. Because every time you have a max or a min, the slope of the line that goes to the max or a min has a 0 slope. M is 0, right? So us not being able to pick m equals 0 because it did not return the equation on the other end, means that immediately our solution is not going to have min and max. Now we know that's all cool because x cubed doesn't have it. We know that tangent function doesn't have it. The e to the x, as you mentioned earlier, doesn't have it. That's okay, right? So us picking m equals 0 and not getting anything back is fine. You just deal with that and you move along with your life to, let's say, pick m equal -1. See what happens there. So if you pick m to be -1, that leads into -1 equals to 1 over x from where x is -1. All right, I'll do two more and that's it. So if we choose m to be -2, we get -2 is 1 over x from where x is equal to -1/2. And finally pick m to be -3, which gives us -3 is 1 over x from where x is equal to -1/3. And that concludes this silly calculation. Now, why do I say silly calculation? Well, we didn't use much of calculus, right? Now what I'm going to do, let me just use my awesome drawing skills over here. There we go. Look at that. All right. And I'm going to choose one unit to be 2 squares so it's larger, so we can actually see it. All right, so that's 1, 2, 3, -1, -2, -3, -1, -2, -3 on the bottom, 1, 2, 3 on the top, and so on. All right. So what do I have? Look, I will create, this is called isocline, but that's for differential equations. At x equals to 1, that's this line. That's x equals to 1. At x equals to 1, I get to draw these small slopes all over this blue line. So the slope of 1 is the 45-degree slope, right? You remember that's the y equals x has a slope of 1. So I get to draw 45-degree slopes along this line. Oh, I'm gonna regret this. I gotta give up on this graph and do it better. I'm going to change the scale over here. I must change the scale. You'll live. Use pencil. All right. What I'm doing now is I'm going to make over here 1 unit to be 4 squares, -1. So now this is where my 1/2 is. This is where my let's say right there is where 1/3 is, because I need those values. On the other side, -1, -1/2, and let's say right here -1/3. I'm going to draw this vertical. So I hope you guys understand that these x equals 1. You know that from algebra. X equals 1, x equals 1/2, x equals -1/2. Those are all vertical lines, and those are these blue lines that I'm drawing right now. So I'm going to draw 6 of these blue lines. Oops. And then we just draw the slopes. So for x equals 1, which is the one at the end, we have the slope of 1. So we draw those 45-degree lines. And then we have at 1/2, the slope was 2, so that's steeper. So we draw steeper. That's too steep. No, don't erase everything. So steeper. And then for the slope at 1/3, remember when x was equal to 1/3, the slope was 3, so that's steeper still. So that's where I'm gonna go really steep like that. So hard to draw this on a tablet. Now on the other side, everything reverses. I have -1 of the slope, so that's gonna be -1 at 45 degrees. And then steeper for 1/2, because the slope is -2. And then steeper still for the slope at -1/3 is slope is -3. So now please look at this. I hope that you see that this works like a funnel. If I start, let's say over here, these lines make the function fall in like this. Do we see that? These lines are actually guiding it to fall down. I hope you can see that motion. And from the other side, it does the same thing, right? So all of these look like want to go like that. Fair? Now, you know what we're going to do? This differential equation is not hard to solve. We can use separation of variables and try to see that this is actually the case, right? So let's do separation of variables real quick to check our answer. So differential equation is dy dx is equal to 1/x. Move dx to the other side by separation of variables. So I have that the dy is equal to 1/x dx. And then we integrate both sides. So on the left, we just have y. You can call it y of x. Now, what's the integral of x to the -1? ln absolute x plus c. Because if you do it on both sides, you have to call one c1. You have to call the other one c2. And then you can subtract one with the other. You get c2 minus c1, which you just call capital C. So that's why you don't need plus c on both sides. You can just put 1. Now we got ln absolute x. Guys, that's that. Bless you. Doesn't this look like ln graph? Of course it is ln graph. Except for that part where ln graphs don't have these things on the left. Right? That's the absolute value. Very good. Now, do you see why that absolute value is important? And every time I correct you in class, you said, well, what's the big deal? Well, there it is, the big deal. Clearly, slope fields tell you that they exist. So now you just make sure that you have those absolute value there because they're not there for decoration. It actually works. Right? So direction fields actually can solve these problems. Remember how, and every problem can be solved this way. The question is, are you able to guess how the function actually looks like? And what is the function that the directional field is telling you it should be? So now, you know, whether you recognized ln x from these drawings or not, that's up to you. Now, we were lucky that this particular differential equation can be solved separation of variables, so we do the both ways, and then you see that they actually match each other. So going back to the basic algebra, you know that you can graph, it's a middle school level, you can graph any function by picking x values, computing y's. You have x and y, you plot x and y, and then you connect the dots, just like in a coloring book, right? You can do that for every single function, regardless of what do you know how the graphs look like. Going on, you also know that not every integral can be integrated with methods you guys learned. Calc 1, Calc 2, doesn't matter. Those integrals have to be solved by numerical methods. So every definite integral can be computed, whether it's exact value using analytical methods, integration by parts or whatever else, or using the numerics. Now, this is the method to solve every differential equation, no matter how it is, how it looks like. But the question is, can you recognize what kind of function you have on the other end? But you know what? You at least have the curve. In many applications, you just want to know if the solution is increasing or decreasing, whether it's stable, whether it's right. So at least it will tell you that if you don't know what the actual function is. So it's a very, very powerful method of solving. And as you can see, it doesn't require any calculus because you are picking this slope to be 1 or 2 or 5 or whatever. And you are computing the rest of the function, which is graphing linear lines, which is algebra. So technically, if the algebra student is able to comprehend this part of the derivative and all that stuff, this is algebra level work. So check that out and do some homework and then come back with questions. And yep. And you can always check your answer if it's something that you can actually solve. Plus, you have Mathematica, so you can solve anything. Type it in. And you're done. That concludes chapter 7. We are going to take a 2-3 minute break, and then we're going to restart everything, start chapter 8, sequences and series. So we do 8.1 and 8.2 today. So let's do it.